Good. So now we understood this current mirror circuit and we want to use it in order to create the so-called differential amplifier, which is a piece of what is called the operational amplifier. So let's discuss this schematic diagram we have here. So at the bottom we have a symbol that basically summarizes this current mirror circuit we studied so far. So this branch here is the one that corresponds to this one here. So the one for which the current is copied. All the rest we keep it aside, hidden in the symbol, because it's not interesting for us to show it at this moment. So I go back here to the slides. Okay. So for us, this one is a branch where the current is regulated at a certain value we call ISS. Okay, so now we have another thing. We have the current mirror circuit here in this upper part, in this green box. But let's notice a thing. So we didn't say one thing when we were studying the MOSFET. So you see this symbol, it has a little arrow coming out indicating the source. So the source of the electrons. So this arrow will indicate the direction of flow of the electrons. Oh, sorry, the formal current actually. And this type transistor was developed in this fashion. So we had a P bulk material and correspondingly a so-called N channel. So this is called NMOS. And MOSFET. So MOSFET of type N. So when the material of the bulk is P, the channel is N. So vice versa, we can manufacture a MOSFET in a complementary way. We put a N-type bulk material, then here we will have P plus wells for the ohmic contacts, and then correspondingly with the N-type material we will have a P channel, so a channel where the carrier of charge are not the electrons but are the holes. So remember that there can be electrons moving in a semiconductor but also holes, which is the vacancy of an electron, with this mechanism of filling a bind, leaving a hole for another electron that will fill the bind, and so on. So there are two complementary technologies, and in fact this is why this thing is called CMOS, complementary MOSFETs. So here we have N-type MOSFET, while here we have, with this other symbol with the arrow pointing inwards, we have a P-type MOSFET. So we don't need to repeat everything for the P-type transistor. It's exactly as the N-type, but the only thing that changes is the direction of the current respect to the voltage, the VDS voltage. So to make a long story short, whatever you do with the transistor connected with the source having a lower value of voltage respect to the drain, you can do with the P-type by exchanging the voltage, the direction of the voltage. So this gives us an advantage, which is that in this case we can assemble such kind of circuit like this, where respect to this box, this thing here is a sort of resistor. Imagine it like this. We know that a transistor is a controlled resistor, so for a given voltage at the gate, there will be a certain resistance between this point and this point. So what we are doing here, we are assembling a mirrored version, sorry for the game, of the current mirror, having a transistor as a resistor. So the current mirror will copy here in this branch the current which is flowing here. So let's call X this current and X this current. Then those two currents will merge here at this node. And for the Kirchhoffs principle, we know that it must go here. And so this ISS current would be equal to X plus X, so to 2X. So it means that this X current is this ISS divided by 2. And this happens when this resistor has a certain value, which has to match the value of the equivalent resistance of this transistor, which is of the same type of this one. So if we drive it with the same voltage gate here, VG, those two resistances are the same. So for this we are sure that this trick works. So what happens now if we do another thing? So now we have to consider which are the inputs and which are the outputs of this device. So this device has two inputs, one is here and one is here, and one output which is here. So it's a black box, I draw it here with two inputs and one output. Maybe you don't see well in this color. Let's change color. So one is called the positive input, the other one is called the negative, and this is called the output. So what we want to do now is to create an imbalance between the two inputs. So for instance, we put a plus delta V on this input and a minus delta V on that input. And we want to see what happens. So from a steady condition where in those two branches the current ISS divided by 2, which is constant, ISS is constant because we put a current sink here, so we assembled such kind of current generator which regulates the currents to be stable at this value. If I increase the voltage here, let's say that for this voltage I have an increase of current here, I call it delta I. Now it's not important how much. So if I raise the voltage, the current will rise in this branch. But this current is also copied here. So it will rise also here. So when I do this, if simultaneously I create an imbalance but negative which basically means that I am creating a differential input, so I am attaching a source of voltage here, for instance. I'm attaching something between this and this, like a battery. So because now I make this negative imbalance here, it means that in this transistor I will have a decreased current, so minus delta E, respect to the bias of ISS divided by 2. And then this thing here still has to be equal to ISS divided by 2, because we calculated this before. So the only possibility to solve this is that out of this node, because of the Kirchhoff principle, a 2 delta I current will exit. Because here, now, because of this imbalance, I will have ISS divided by 2 plus delta I. Here I will have ISS divided by 2 minus delta I, and the summation of the two makes exactly ISS. So this is cancelled with this, and ISS plus ISS half, IS half plus ISS half makes ISS. So this equation is satisfied. But if I apply the Kirchhoff principle at the B node, so I have one entering current, which is ISS half plus delta I, and one exiting current, which is ISS half minus delta I. Because the algebraic summation of the entering and exiting current of a node should make 0, it means that the current that should exit from this node is 2 delta I. Then there is a resistor here, so this current flows in a resistor, and so it will produce a certain voltage at the output, which is according to the Ohm's law. V out equals R, this R, multiplied the current, this current, to delta I. And so according to the value of R I can choose in this circuit, I can make this output to be smaller or bigger than the cause that created it, which is this imbalance of gate voltage delta V. So I created a system where the input is 2 delta V, so let's call it delta V prime. This is the input, and the output is a constant multiplied delta I, and we know that this delta I is something that somehow is related to the gate, because this is something like GM VGS, and this thing is related to delta V prime, which is the input. So this thing is an amplifier that amplifies not one input, but the difference between two inputs, and creates a corresponding output with a certain amplification factor, which is called the gain. Now we have this extension of this circuit, so we see the current sink, the current mirror, the differential amplifier, and we attach another thing which is called the output amplifier, which is this green box here, to this output where we had this resistor transforming the 2 delta I current into a voltage. So we apply this voltage to the gate of this thing, and this is a sort of voltage divider where the values of the two resistors are controlled in terms of the fact that they are transistors. So the gate voltage here will control the value of the internal resistance of the transistor. So those two resistors, because of this connection here, they are working in a complementary way. We say that if the signal grows at the gate here, the resistance of the lower transistor will decrease. So we say it gets into conduction. While for this one is the opposite, the resistance of this one increases. So when we have a voltage divider like this, where this resistance, I call it R low, and this I call it R high. Sorry, high doesn't mean that this is above this, it means that the value of R is higher than this one. And here I have my VCC, which is this thing. We know how to compute the voltage at the output V out. We studied this. We said that for a voltage divider, V output is V input multiplied, in this case, R high divided R low plus R high. So if okay, let's say like this. No, sorry, I made a mistake. So it's like this, but R2 is this one, is R low. Okay. So when this value of R low gets very low, so when the gate voltage here, VG, is so high, for which the channel of this transistor is so open that a lot of current will flow in it, so the resistance of this transistor is very low, let's say 0. So here I have something like V input multiplied, say 0 over 0 plus something. This thing makes 0 multiplied by an input, it makes the output to be 0. So when the signal is high here, the output is low, let's say 0. Now it's not 0, but it's -5, because we applied a secondary voltage source here. So we bias this transistor not with the ground, but with a negative voltage respect to it, which means that from this node to this one there is a battery connected with this polarity. So the minus is here, while from this point to the ground there is a battery connected with this polarity. So this thing is called plus VCC usually, and this thing is called minus VCC. So when this happens, for a high voltage here we have a low voltage here, and we can repeat the same thing and study what happens if I put a low voltage here. I will have a high voltage here. So this thing is a sort of inverter. It inverts the voltage. I mean the output respect to the input. So this is called output amplifier because then this voltage is coming from the result of a quite strong current flowing in these two transistors. And this allows us to drive various type of loads which can be of a low value of resistance, for instance. And because this current is sufficiently high, it means that this will be able to make current flowing in this resistor, even if the value of this resistor is quite low. And because the gate of the transistor is not really a direct connection, so remember that here we had a sort of insulating layer of oxide, so the current that flows at the output doesn't affect whatever is happening on the other side, because there is no electrical connection basically. So it means that even a weak voltage here, which basically makes no current flowing from the gate to other parts of the transistor, is able to control a possibly big current. So this is called also current amplifier. All this thing is summarized in a symbol here, which is this. So it's a triangle. So we put the plus input and the minus input, which are those two things here. We say that there is a plus voltage for the positive supply and a minus voltage for the negative supply, and one output, which is this one. So this thing is called operational amplifier. You can imagine that once you have this, you can replicate it and you can cascade it. So you can put other circuits like this, one after the other one. Why we want to do this? Because if we do this, the amplification factor will increase. So if I have such kind of situation, like a black box with an input, then I say like this, and something that multiplies the input by a certain factor, let's say 10 times. So if I take this and I put another one like this, then the output prime is equal to 100 times the input. So repeating this in a chain, I can create amplifiers with a very big gain. So ideally, an ideal amplifier, operational amplifier, is done in a way that inside it has circuits similar to these ones, say inside this triangular symbol, providing us such kind of characteristics. The amplification factor is pushed to, let's say, to the limit of infinitive. Of course, it's not possible. Usually this coefficient is something like 10 to the power of 8. In the ideal case, it would be infinitive. The input impedance is something that approaches also, let's say, infinitive. It's not like this, of course, but most of the time it's something like 2 to the 12 ohms, something like this. So what does it mean? It means that from the point of view of the current entering the inputs, basically there is no current entering in the inputs. Why? How do we see this? With the Ohm's law. So if Here we have a sort of, let's say, resistor that connects the input to whatever is after the input. And remember, there is this insulated layer of silicon dioxide. So if V equals R multiplied I, it means that I equals V over R. We can say V over Z to be more generic with impedance. By saying that the impedance is very high, the input impedance is very high, so we are basically saying that there is a voltage at the input but no current is entering. This is a very good characteristic because it means that we can sense the voltage of something without affecting our thing that we are observing. Imagine, for instance, we have something very delicate like a neural cell, a neuron, that is producing a very weak signal, and we would like to measure the value of that membrane potential here at the neuron without interfering with the neuron. It means that we need to have an amplifier with a very high input impedance. So this is why we want to have MOSFETs and such kind of things. On the other hand, after the signal has been amplified, we want the signal to be able to drive something, for instance, a recording system or whatever. So we want our amplifier to be able to deliver this signal to something else. One thing we can desire is to have the output impedance of this device to be approaching to zero. It's not zero, of course. So zero means that if we consider the Ohm's law, V equals R multiplied I, let's write it Z multiply I. So if we compute the output current I is equal to V, the output voltage, divided Z. If the output impedance is zero, then I goes to infinitive in the limit. It means that this thing is able to drive whatever load we want to be attached at the output for the same output voltage, which is what is desirable. In practice, the impedance is not zero of the output, but it's something in the range of ohms. So it can be small, but of course not zero. This is a theoretical case. The output of this guy goes according to this equation. It's a differential amplifier with an amplification factor of A. So it takes the difference of the two inputs, V plus and V minus, it multiplies by a coefficient A, which is very big, and this is our output. Okay, so now we have to understand what is the ultimate reason for which we want to create such kind of amplifier with this basic fundamental characteristics. A very high gain, a very high input impedance. We kind of understood why. We want to be able to amplify things without interfering with the things we are amplifying. A low output impedance is good because it means that we can deliver the signal to something. This is the differential equation, the equation that regulates the differential inputs. We have to understand why we need a very high amplification factor. So the solution to this question comes from this circuit. It's one simple circuit which is called the non-inverting operational amplifier configuration or circuit. So let's consider this. Now we are not drawing the plus VCC and minus VCC batteries, just for simplicity. So we assume this thing is powered up by something and everything is connected as it should. We consider an input connected to the plus input, and then we have this connection which is called feedback from the output back to the input through a voltage divider like this. So in order to understand how this works, we have to do some calculations. So we have to write the equations we know that are valid for this operational amplifier. So the output equals a certain coefficient A multiplied the difference of the two inputs. Then we have to inspect the circuit. So the plus input is connected to a signal of interest which is called V input. This is what we want to amplify. While the minus input is connected as the output of a voltage divider made by those two resistors, RF, R feedback, and R. And this voltage divider is powered up not by VCC but V output. So we know how to solve this voltage divider, and we can calculate that V minus is this. We know it's this because the input of the operational amplifier has a very high input impedance. So it means that there is a sort of resistance that goes here connected to something, but this thing is very, very, very big. So if this resistor goes in parallel to this, for instance, because we have studied the series and the parallel circuit, when a very big resistor goes in parallel to a certain resistor, basically this thing doesn't count. It's like, you can say in a simple words, so if this resistance is very, very, very big, it means it's an open circuit. So it's another way to say that this thing is not present. Okay, so we compute V minus. Then we can substitute V plus into this and V minus into that. And we obtain an equation which is V out equals A multiplied V in minus R over R plus RF V out. So we can develop a little bit this equation, and we find that V out equals A VE minus A R over R plus RF V out. Then we bring this term on the other side, and we get V out equals V out multiplied 1 plus A R plus RF equals A VI, and then I can compute the ratio between the output V out and the input V out of this equation. So what I get is this, and it's called the gain of this amplifier, and it's this thing. So now the beautiful thing is that if the original operational amplifier had a very high A gain, which is also called open loop gain, let's say something like 10 to the 8. So then if you compute the limit of this ratio V out over V in, which we call G, for A that goes to plus infinitive, you can easily do this with the L'Hopital rule. This limit is this, that we can write also like that. So we found a way of building an amplifier with a very high input impedance, a very low input impedance, and a gain factor which is what we want, defined only by, let's say, programmed. The gain is programmed by those two resistors. And another beautiful thing is that this gain does not depend on the internal gain of this amplifier if this open loop gain is very high. It means that in principle, if this gain A was depending on some parameters like temperature, voltages, currents, whatever, so if this A function was not linear, in this circuit it doesn't matter, because the value of the gain of this circuit does not depend on A if A is big. So we transform an ugly amplifier in a very beautiful linear amplifier. I mean linear because this G is constant and it depends only on the value of those two resistors. So this is why operational amplifiers are beautiful and very useful in electronics, because basically they are ideal amplifiers that you can program with the gain you need.